At Harvard, a Danish scientist, Lena Howe, had the idea of using a condensate to slow down light.
We all have this sense, light is something that nothing goes faster than light in vacuum. And if somehow we could use this system to get light down to, to a human level, I thought that was just absolutely fascinating.
Lena Howe created a cigar-shaped Bose-Einstein condensate to carry out her experiment. She fired a light pulse into the cloud. The speed of light is around 186,000 miles per second, but when the pulse hits the condensate, it slows down to the speed of a bicycle.
So the light pulse might start out being 1 to 2 miles long in free space. It goes into our medium. And since the front edge enters first, that will slow down. The back edge is still in free space. That'll catch up, and that'll create that compression. And it'll end up being compressed from 1 to 2 miles down to 0.001 micron, or even smaller than that. You could say, well, gee, it's easy to stop light because I could just set a laser beam into a wall and I would stop it. Well, the problem is you lose the information because it turns into heat. You can never get that information back. In our case, when we stop it, the information is not lost because that's stored in the medium. And then when we have time to revive it, the system has all the information to revive the light pulse and it can move on.
One day, ultra-cold atoms will probably be used to store and even process information. Even now, cold atoms are being turned into prototype quantum computers.
As a quantum mechanic, I engineer atoms. To make a computer out of atoms, you have to somehow get atoms to register information and then to process it. Why build quantum computers? Because they're cool. It's fun, and we can do it. Right? I mean, we actually can take atoms, and if we ask them nicely, they'll compute. That's a lot of fun. I mean, have you ever talked to an atom recently and had it talk back? It's great. Yes, look at that.
Unlike ordinary computers, where each decision is based around a bit of information and is either a 0 or a 1, in the quantum world, the rules change.
At first glance, a quantum computer looks almost exactly the same. But quantum mechanics is weird. It's funky, okay? It's weird.
When you do quantum computing, you want to make this weirdness work for you.
So now let's look at our quantum bit, or qubit.
A qubit can not only be a 0 or a 1, it can also both be a
0 and 1 at the same time. It's almost like a form of parallel computation, but in a parallel computer, one processor does this, one processor does that. So you have two processors doing this and that. In a quantum computer, you have only one processor that's doing this and that at the same time.